who featured very heavily in my talk, Jean-Marie Maillard. Thanks for me.
Well, thank you, Marie and Vladimir, for enabling me to give this talk and pay my tribute to Rodney. This was important for me. I'd like to say that I first met Rodney in Ireland in Enschede in the 80s, and after 2 years, maybe 1 year and a half, he invited me in Canberra for, well, for me, it was really a 3 months dream visit. This was my first visit in Canberra. There were many others. And the last time I saw Rodney, it was in London at the Royal Society. And in between, as you mentioned, we had so many conferences in Palm Cove, in, well, lovely dream places, on this small planet. In particular, we had this conference in Paris, and Marie, you were kind enough to tell me that this book was in good place in Rodney's office. In all these conferences, I gave many times talks underlying basically this, that the Young-Baxter equations are necessarily parameterized in algebraic varieties. So even if you don't like algebraic geometry, you have algebraic varieties, and these are not any algebraic varieties. These are algebraic varieties with an infinite set of birational automorphisms coming from the inversion relation and combined with some symmetries. And actually, this explained so here you have a surface, an abelian surface, but in the case of the curves, it explained why you have to deal with genus 1 elliptic curves. So that's the reason why you have so many elliptic curves in the Young-Baxter solutions. And you can actually get these algebraic varieties by the iteration of these birational transformations. But I'm not good. So for instance, in the case of Baxter model, Vladimir mentioned this parameterization of the Baxter model. So you can write the 4 homogeneous variables A, B, C, D in terms of a spectral parameter V, some shift on the elliptic curve, eta, and the modulus of the elliptic curve. The modulus of the elliptic curve is clearly a very important constant. Okay, so typically the iteration of the birational transformation in that case, in the case of Baxter model, corresponds to a shift. V gives V plus n times n is an integer, n times this shift. But K, the modulus remain fixed. Okay, so I'm not going to talk about these symmetries in the spectral parameters, but on the contrary, I'm going to talk of transformation in K is modulus. And the spoiler, this will correspond to the renormalization group, an exact representation of the renormalization group in the case of the Baxter model, for instance, or model with elliptic parameterization. So you may know that in general, partial function of the IZ model, subcase of Baxter model, is given by a double integral, but in fact, at the end of the day, this is nothing but a hypergeometric 4f3 hypergeometric like this here. And here, the pullback, the variable, is a square of the London transformation of the modulus K, the elliptic modulus K. Okay, so here we see that the London transformation pops out naturally. So this is a more traditional way of writing the partial function as double integral, and on that form, it's not really clear that partition function is solution of linear differential equations. In jargon of mathematicians, it's called definite. When you write it as a 4f3 hypergeometric function, it's clearly definite. The solution of linear differential equation is a bit less clear. But in fact, if you perform some derivative of this form, you'll get something which looks like the form of all the lattice green functions. And lattice green functions are also diagonal of rational functions. I'm not going to explain what are diagonal of rational functions. I don't have time. But if you're diagonal of rational functions, then necessarily you are definite, the solution of linear differential equations. And most of the N4 integral you have in physics are diagonal of rational functions. And this is the reason why you have zillions of arithmetic and number theory property popping out in physics, like the critical exponents are rational numbers, the series are so-called in mathematical jargon, globally nilpotent, that is to say, it can be recast into series with integer coefficients. And these series are such that if you look at them modulo prime, they become algebraic function, which is a bit surprising. So you have a lot of magic arithmetic number theory properties coming in physics, but once you realize that there are diagonal of rational functions, you understand why you have all these number theory popping out. In the case of Baxter model, the expression of partition function was given by Rodney under that form where you have infinite product of infinite products. Okay, one corresponds to this iteration of these birational transformations I mentioned. This is one of the infinite product, and the other one corresponds to say, oh, we have elliptic functions, and we are performing an infinite product of elliptic functions. Okay, these are under that form given in terms of three variables, q, x, and z. Q is the ratio of the two periods of the elliptic functions, and x is essentially the exponential of shift, and z is the exponential of the vector parameter. And with that form, the three variables q, x, and z, I'm not going to say they play the same role, but they are almost on the same footing. At least q and x are quite on the same footing. And okay, there's under that form, you might say, okay, we have three periods, but we know that function of one complex variable can have only two periods. The third one is not a period. It's a quasi-period, again, corresponds to this automorphy property coming from the inversion relation combined to the symmetries. Okay, let me recall that the q equal x to the 4 is the Ising model. Q equal x to the 5 is the hard hexagon model. And q equal x to the r is an integer, corresponds to the RSOS model. Okay, so let's have a look at the magnetization of Baxter model. It has this lovely infinite product form in terms of the known q. This is certainly not going to be definite in Q, but if you actually rewrite it in terms of the modulus of the elliptic function, so of course going from the known to Q to the modulus K, it's a transcendental transformation. In Maple, it's called elliptic modulus or elliptic known. You go from one to another one. Things become algebraic. And so when you are algebraic, you'll define your solution of linear differential equation. Okay, I'm not going to talk to string theory, Calabi-Yau, and things like that, and mirror symmetries. But here with this two representation in the norm or in the modulus, you have the toy example of a mirror symmetry and mirror transformation. And in fact, we'll see that you need the two representations. There are two complementary representations, and we need the two to understand how things work. In one, in the norm, you understand the modular group properties, but you're not able to see that you're definite. And the other one, you see clearly you're definite, but the modular group properties are a bit mysterious. You need the two description. Okay, let's have a look at the polarization of the Baxter model. That is infinite product closed formula. Well, let me just give you the result. If you X and Q are commensurate, that is to say some X to an integer is equal to the norm to another integer, then the polarization will actually be algebraic and you'll be definite. But again, it's not clear. And this expression is certainly not definite in the node, in Q. Okay, so here I'm talking in fact of these for the one who know a bit of mirror symmetries and so on. These are famous series expansion X, even as a series in Q, and here you see integers. And here the norm is expressed in terms of the X variable, again, integers, and going from Q to X or X to Q is a transcendental transformation. Actually, it's differentially algebraic, and we'll see we have a Schwarzian equation, but okay, we'll come to this later. So in fact, as I said previously, we need the two representation in K and in the norm. Let's take something, well, not so simple example. The Ising model, everybody believes that everything is known on the Ising model. No, that's far from true. If you look at the full susceptibility of the Ising model, this full susceptibility can be written as an infinite sum of n-fold integrals, the so-called chi-n's. And these chi-n's are actually diagonal of rational functions. But the full susceptibility is a very complex function. Actually, we have a natural boundary, and it's not even clear if the full susceptibility is differentially algebraic. Differentially algebraic, again, in mathematical jargon, it means that your solution of a nonlinear differential equation. Okay, just in a few words, once you know that you have diagonal rational functions, you get zillions of arithmetic properties. Critical exponents are rational, etc., etc. And in particular, the series expansions can be recast into series expansions with integer coefficients. And when you look at the series modulo primes, they become algebraic. Pretty funny. You'd expect to do some physics, everything is supposed to be dirty. Well, no, you are really doing number theory like Monsieur Jourdain doing prose without knowing it. Let's look at these chi-n's. These chi-n's are solution of linear differential operator of very high order, or chi5, or even that. Chi6, you get order like 50, 60, 80, okay, very large order. But these operators are actually direct sums of products of, well, small factors, operators like that. It can be on 2, 3, 8, blah, blah, blah. And the solutions of all these factors are highly selected solutions, like elliptic functions, modular forms, derivative of modular forms, and so on. We have a lot of modular properties. Let's try to understand that. So you might say, okay, what are modular forms? At this step, let's say that modular forms are just posh, snobbish elliptic functions. They are automorphic forms. Namely, you have a function, you have a symmetry, x becomes y of x, and your function for this new pullback, this new symmetry here is, well, your function is not invariant, it's covariant, and here you have a factor you can describe. It will be algebraic also. This is what Poincaré and this old mathematician called automorphic functions. Okay, we have some automorphic property on the functions. That's the simplest example of symmetry, in fact. Symmetry on function. Spoiler, the symmetry we have in mind are going to be exact representation of the renormalization group. Okay, here is an example. It says that's true life. We're corresponding to chi3 and chi5. Okay, maybe it's not very illuminating, but it's okay. Between the mathematical description, which is always elegant because you don't give an example in true life in physics, okay, this complexity. Let's have a look at the some expansion in some well-suited variable of the full susceptibility. Here it is. And as I said, it can be seen as a sum of an infinite number of n-fold integrals. The simplest one is chi2 here, and chi2 has an expression as a hypergeometric function, which is here. If you compare these two series, they are very, very, very close. If you're not too picky, you might say that chi2 is, well, a pretty good approximation of the full susceptibility. You know that full susceptibility is really a complicated function. But if you're not too picky, chi2 is a good approximation of this full susceptibility. And with that example, we are going to see that we don't have exactly the automorphic form I mentioned at first sight, but a slight generalization, namely that your function changed by your symmetry will be your function with some linear operator acting on that function. Okay, in our case, chi2, well, that's what you get. You have a modular form. This is a modular form here, and you have another one operator acting on this modular form. So we have a slight generalization of the automorphy property. In Keynes' modulus, here you do see the London transformation on the modulus. Here you have your function, chi2 of k, and you have a derivative. If you write it conversely, you can write chi2 of k as chi2 of the London transformation with another one operator. And when you see that, you can clearly iterate again and again. And if you recall that this transformation, when you iterate it, starting from a k value of the elliptic modulus, you will convert to k equal 1, which is a critical point for the model or the Ising model, and so on and so on. So you have exactly a functional equation, which is an exact representation of the renormalization group. Okay. So at first sight, you might say, okay, well, what is an exact representation of the renormalization group? You have the critical point, k equal 1. You have two other critical points, k equal 0, k equal infinity, which are trivial 1. And you have to preserve these three critical points. When you perform your iteration, starting from three critical points, at first sight, you have in mind you are going to create zillions of other critical points. No, you want to stick with just these 3 1. So that's a strong constraint. An exact representation of the renormalization group cannot be anything. Furthermore, if you have in mind that, okay, we have elliptic functions here, we have an elliptic parameterization of our Baxter model or Ising model or Young-Baxter integral model, you have to be compatible with this elliptic structure, elliptic function structure, in particular the lattice of periods. And if you ask that you preserve these 3 points and you preserve the lattice of period, you are talking, in fact, of the isogenies of the elliptic functions, which is a narrow set. So we know exactly what are the exact representation of the renormalization groups. These are the isogenies. And in fact, we are talking of what is called the modular correspondence. So we are going to talk about that. Okay, so let me just recall that here we don't have exactly what we expect is, that is to say, a function, we change the modulus into the London modulus, and we get the same function up to a factor, but we have a slight generalization with derivative. But remember, the simplest example of such automorphic functional equations corresponds to the complete elliptic integral of first kind, elliptic K, where you have this functional equation. Okay. So with the Ising model, we saw that we have a lot of factors and elliptic functions, modular forms or derivative of modular forms popping out, and we want to understand this modular form. So that's what we are going to do. Crash course on modular forms. Let's consider this second order linear operator. It has the following 2f1 hypergeometric solution. And this solution can be written in 2 ways with the same function, but different pullbacks. Okay, here you have one pullback, here you have another one, up to a factor. So that's really the kind of automorphic property I was mentioning. It looks like one identity, but of course, if you combine this identity with itself, you'll get an infinite number of identities. So that's a strong structure. These are the 2 pullbacks. And if you eliminate T, for instance, you get these algebraic relations between X and Y. So if you, I didn't mind, what is this? X gives Y of X symmetry. Well, it's given by this algebraic formula. This is a modular curve. This is the fundamental modular curve. And more generally, you will have this kind of structure, namely the 2f1 of Y, the same 2f1 of X, a factor, and we can combine them and get an infinite number of identities. Another parameterization, if you introduce the J invariant of the elliptic curve, you can write X like that, Y like this, where we have changed K into the modulus of the London modulus. So we have exactly the same algebraic modular curve, fundamental modular curve, which is in fact a representation, an algebraic representation of the London transformation. But if you remember this fundamental modular curve, it was symmetric in X and Y. So going from X to Y or Y to X, that's a thing that's reversible. Okay, so in fact, we have a representation of London transformation, but also of the inverse London transformation. That's interesting as far as a renormalization group is concerned. In general, people see renormalization group as a semi-group. You have an arrow of time, you iterate and you go to K equal 1, but It's like going to a black hole, but you cannot go extract yourself from a black hole. No, it's perfectly reversible. Renormalization group generators are reversible, but the price to pay is that you have to play with algebraic transformations. You're multi-valued, as mathematicians used to say in the old time. People don't talk of multi-valued functions anymore, but okay. You're reversible if you keep in mind that you are multi-valued. You have algebraic transformations. Okay, if you want to see what these modular correspondence are, well, let's write explicitly as a series, which is the solution of y as a function of x. You get these two series. Okay. Okay, many more examples with other pullbacks and the corresponding series. So these are other modular correspondence, and you see that there's this series and it's compositionally inverse. Okay, one with t to the 5. And here an interesting example with t and t to the 4. So these are the two fallbacks. You get another modular curve, but when you look at the solution, y as a function of x as a series, you get something like x to the 4 plus other terms, which are integers. Another series, which is a compositionally inverse of that previous one, but also a quite curious one, which is an involutive series. It's, if you combine this series with itself, you get the identity. This series is not very often mentioned in for modular correspondence, but that's actually a series which is the analytical continuation of the other one. Okay, if you want to understand this third series, let's come back to the original series corresponding to the fundamental modular curve. We had something like x squared plus blah, 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 or square root of x plus blah, 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 up to a plus or minus sign here. Clearly, the last one, x to the 4 plus, is a combination of x2 with itself. This one is a combination of x to the 1 half with x to the 1 half. And the quite mysterious involutive series correspond to this composition. Okay. Again, the general framework. If we introduce such a function here, so we take the function to the square and up to a factor here, this automorphic property on top is actually a relation on the one form like that. And if you eliminate the factor, so here we have this A of x factor here. If we eliminate this A of x, for instance, is in corresponding linear differential operator, we get a condition only on the symmetry on y of x. And we see that y of x is a solution of the Schwarzian differential algebraic equation. W is a function of the f I wrote before in red. So you have second derivative over f, blah, blah, blah. At first sight, you say, okay, this should be highly transcendental. We are calculating a derivative of a hypergeometric function divided by a hypergeometric function, should be a mess. In fact, it's a rational function, curiously. And I recall the Schwarzian equation. This is interesting because this Schwarzian equation coincides exactly with one of the condition obtained by Casal in a much larger mathematical framework corresponding to so-called grouping a generalization of group that I'm not going to talk about that. But what we see is that all these modular correspondence, the infinite number of modular correspondence, I gave you some explicit example, they are actually solution of the same Schwarzian equation. So this Schwarzian equation, very simple to write, is actually like a Pandora box. It contains an infinite number, all the modular correspondences. And question is, are all the solutions to modular equations only modular correspondence? That's the $1,000 question. Okay, let's have a look at the Schwarzian equation. We are physicists, so we do perturbation theory. We try to get something in X or A of X plus something. Well, we can get order by order a solution depending now on one parameter called A. And this series, which clearly is not of the type of the modular correspondence before, so it's straight. We want to understand that series. This one parameter series is a series of commuting series here. So we have something which is called also replicable functions. These functions can combine together and so on. Let's take some limit of this series. A goes to 0 limit. Well, we recover the first series I mentioned at the beginning of my talk, and taking the A goes to infinity limit, we get the other series, X tilde. And we can actually see that this one parameter series is just this combination. In fact, if you take the A equal 1 limit, if you remark, then we have A minus 1 in all these different genes from in all these coefficients. What will remain is just X. In fact, the two tilde, the known Q and X tilde, they are inverse compositional necessarily. So here we have a conjugation, a simple conjugation. Q and X are differentially algebraic. They are solution also of Schwarzian equation. And all the modular correspondence I mentioned can be expressed quite simply in terms of these X and Q. And in fact, you can actually understand that if you combine all these this series, when A is an nth root of unity, will actually also be modular correspondence and solutions of the Schwarzian equation and so on for any A nth root of unity. One more comment. If you look at this series for A, an integer, you see that this series is clearly a series with integer coefficients, and it's differentially algebraic. So my conclusion, well, I have to skip for a really important result, but okay, that's life. With that series, you see that you get a one parameter series, which is such that for A, an nth root of unity, you get algebraic functions. And for A, an integer, you get power series with integer coefficients which are differentially algebraic, which is something that's so easy to get. Let me recall that in the as far as I'm concerned, if you look at the lambda so a lot remains to understand on differentially on power series solution of selected differentially algebraic equation. In fact, so many people believe that nothing can be done on nonlinear equation. It's so placed in the zoo or forget. No, that's not the case. As far as globally bounded differentially algebraic series are concerned, to use the word of Rodney, this is a defeatist nonsense. And finally, I would like to say so many times people ask, okay, what is mathematical physics about? Is it useful? Okay, so Fourier believes that the main goal of mathematics is being used to the public and explain natural phenomena. But a philosopher like him should know. So this is a letter of Jacobi to Adrien Legendre, that the only goal of science is the honor of the human spirit. And that question of numbers is as important as a question about the world system. And this is a photo of Rodney at the Royal Society, and I let you guess who is on painting. Isaac Newton. Yes, that's it.